Good afternoon, everybody. Hope everybody is having fun at reInvent. I'm extremely excited to be here and share the stage with Axel, who will come here shortly to talk about how is Whirlpool democratizing the entire virtual product development with AWS. And before Axel comes in, I will take a few minutes just to talk about what is AWS doing in this entire product development, simulation, and product engineering space. And how are we helping our customers transform their product engineering landscape? If you look at the industry trends from a product engineering perspective, there are three major trends which is right now impacting the industry. The first one being, as you know, most of the industrial manufacturing companies, most of the discrete manufacturing companies, they are no more just manufacturing or designing traditional discrete products which are disconnected. These days, all these products are connected, they are smart, which means, you are not just selling a product, but you are selling a product and a service with that because these are connected products. Second, because these are connected products, the entire engineering landscape is becoming more and more complex. And what I mean by that is you are no more just doing mechanical design or electrical design or electronics design, but you're also doing a lot of embedded software design. You're also looking at connectivity as an example. And hence the entire engineering landscape is becoming very complex. And that leads to longer lead times to design new products, to engineer new products. And then last but not the least, given the market is so competitive, there is a lot of pressure to reduce your cost of, the cost of developing a new product, right? You really want to make sure that for you to be competitive, you are continuously focused on optimizing your cost, not just to develop the product, but also optimize your cost of quality. And this is what every single customer I talk to every single day is going through, these three trends. So what does this mean? Like, how is AWS helping our customers solve some of this and also accelerate their journey? From an AWS perspective, we offer 200 plus services, right, across multiple use cases. From a product engineering perspective, if you look at these four boxes across CAD, across CAE, across PLM, across EDA, typically what you would see in any manufacturing customer, these are very disconnected, siloed systems. And what AWS is doing with the customers is to really help build that gap so that you're no more disconnected, but you are unlocking your data silos by leveraging AWS to not just migrate these different applications, different platforms to AWS, but also modernize, because that's where you start unlocking real value in terms of faster time to market, reducing the total time it takes to design new products. And more importantly, once you start leveraging AWS as a platform to design new products, now you can start using a lot of AWS Gen AI capabilities. For example, you can start using Bedrock as a platform to build new Gen AI applications, which could be around digital threads, digital twins, and I can go on and on and on. So why AWS? What makes AWS so unique and different in the space? It really starts with, if you're designing new products, if you're into a simulation space, you need flexibility to really scale up and scale down your infrastructure. Because as you are testing new products, as you're doing performance testing, as you're doing load testing, you need that flexibility. Now, you don't need that high infrastructure across 12 months in a year. You maybe need it for 2 months. But for 2 months to be able to scale up, do all the testing, and then scale down so that you're not incurring the cost is what makes AWS so unique. Second, once you are leveraging AWS for your product development, now you have access to a lot of AWS unique capabilities across HPC, AI, ML, so to really start leveraging the power of data, which you have now unlocked, and start using that data to build more and more additional capabilities and additional use cases. Third, it's really about, because AWS offers you so many different options in terms of how you can configure your infrastructure, it really gives you more flexibility in terms of various ways you can optimize your cost to run your simulation scenarios, to run your engineering scenarios. And then last but not the least, it really helps you unlock your data silos. Because at the end of it, data is what helps you then do more modernization, more transformation, and really makes you unique in the market. With that, I will request Axel to come in and talk about the Whirlpool story. Thank you.
Yes, sir. All right, I believe I'm audible to everyone. Thumbs up. Good, thank you. Thanks everyone for being here, for the opportunity to be here and share a little bit about our story, our journey in terms of virtual product development, the way we democratize the knowledge within models so that you can expedite product development with excellence. This is a brief agenda on what we are going to talk today. There will be an introduction to the company. Then we are going to delve into one of the categories, that's refrigeration. Okay, we're going to talk how do we create the right architecture for an appliance here. In this case, refrigerator, in terms of purpose, scoping, and implementation. We are going to delve into virtual simulation capabilities and system requirements here a little bit. How do we do that in a virtual world in order to really expedite this whole process? Solution space exploration is the way that we obtain the data using simulation so that we can use that data to produce models, machine learning models, and do optimizations up front. The core of this talk is going to be the cloud architecture diagrams, and then a video demonstration to wrap that up everything here, and at the end, the benefit, what's in there for us. Okay, about Whirlpool. Whirlpool is a leading home appliance company in constant pursuit for improving life at home. Those are our iconic brands, as you can see, Whirlpool itself, KitchenAid, Genair, Maytag, Amana, Brastemp console, and InSinkErator. With iconic products, as you can see, built-in refrigerators, wall ovens, dishwashers, fully automatic coffee makers, espresso machines, And in terms of value, last year we reported 17 billion in terms of annual sales or revenue. And we have around 44,000 employees across the globe, with around 40 manufacturing plus product development or technology research centers. In terms of the purpose, scope, and implementation, why we are doing this? It's very hard to get the translation of the system optimization in terms of system level requirements and to really harmonize those requirements and deliver on such an emergent type of appliance, that is best in terms of performance, which is translating to the least cost and the best performance. Okay, I'm going to translate performance up front here, but that's the challenge here, okay, because traditional methods are fragmented. And we can do this manually without surrogate models, without machine learning, without Six Sigma, but there will be suboptimal solutions being delivered based on that. And therefore, the company is going to lose because that's not such a winning architecture. The what here is a multi-objective or multi-criteria type of optimization framework across multiple requirements. As you can see here, I have energy, capacity, cooling robustness, noise, vibration, harshness. And also structural and manufacturing simulations. Okay, I'm going to go in more details in the next slide. Just bear with me for a second. And the how. A lot of systems engineering, model-based systems engineering, and design for Six Sigma, because we want to have a robust architecture. How can we be resilient, robust in terms of the architecture definition? That's the foundation, the core that we have. Even for strategic sampling plans, we use the FSS approach here. Validated simulation models, I'm going to show what validation stands for. That's different from verification here, very important concept. And then surrogate modeling is pretty much an equation, a regression model that's based on simulation work, okay? And the two last bullets about how to expedite this whole process in terms of model fitting or training plus tuning within AWS SageMaker. And last but not least, how to democratize these using elastic beanstalk within AWS. All right, so this is not data governance medallion type of governance, okay? This is the way that we assess the maturity or fidelity of simulation models. First of all, we have developmental models, We are trying to understand if something can be simulated. Okay, can I do a fluid dynamics, an airflow distribution inside a refrigerator? Yes, we can. Can I do a taste and odor for ice and water? Simulate that? Maybe not using specific softwares, right? And there are a lot of talks about intractable physics as well. They are deemed to not be simulatable, okay? So we have this distinction. Whenever we pass this gate that, okay, this is simulatable, we have the right assets in terms of software to do that so, then what we're gonna do? We're gonna create the models. That's the layer, the bronze layer that's directional. What's a directional model here from a simulation perspective? Can we do, it's a simulation which is well crafted in a computer software, okay? And we run a sensitivity analysis. That means we are playing with different design parameters and it's following physics, okay? If you change the thickness from A to B, the stiffness is going to change, the deflection is going to change for a fully supported beam, for instance, you know? It's following first principles of physics, okay? The next layer is going to be the silver layer here, where it's quantifiable. Quantifiable is a bridge to get into the validated stage. Why I'm saying that? Because from the quantifiable on is from where we are socializing the simulation models with physical test data. We collect a lot of data from physical testing in order to really cross-pollinate that data back to the simulation models, update the simulation models, and then see if there's such a good degree of accuracy. But the quantifiable stage here is for a limited inference space. It's not for all the architecture, all the product variants. We get one or a couple of families of products, and we do this quantifiable checking, okay? And you can guess what? When we reach the validation stage, it's for all the architectures, okay? Or all the underlying complexity of our systems or appliances here. It's not only for the sake of delivering this, for the sake of obtaining such a good accuracy, as per our rules, right? We need to pass this threshold in terms of accuracy, simulation versus physical tests to have a match with good accuracy, but also we must have high agreement with all the affected stakeholders for this process, because validation is pretty much making the right things from a systems engineering standpoint. What's the right thing here? Simulation must replace physical test, okay? That's the ground rule here. Simulation is good enough to replace physical. And if you do that, you can guess what happens, right? Everything is gonna flow naturally because you can create our own data proactively, right? I no longer need physical. And I can use some strategic sampling plans to really allow us to expedite the construction of machine learning models up front. All right? So I'm going to talk about multiple requirements here, how we crafted this whole inference space that's multi-objective, that's pretty much translating to that. It takes a lot of response variables, or big Ys that we call at the system level, or voice of engineering. The first one is as simple as the internal capacity. Okay? You measure the volume inside those enclosed, or those liners, or the interior compartments of the fridge, the freezer, and in a refrigerator. As you can see here, this is a side-by-side model. We have on the left-hand side the freezer, and there's a vertical mullion that, by the way, you can vary the position. That's a design parameter, right? And on the right-hand side, we have the refrigerator compartment. The model has to really deliver, or to show exactly that the measure capacity is matching the CAD or a physical measurement. Okay, that's a validation for this. Very trivial, but it's very useful because it makes the difference in the trade space. Whenever you want to understand how can you boost internal capacity and deliver energy and deliver other response variables here accordingly. All right, the next one is an intertwined connection between a coefficient of performance from a refrigeration circuit standpoint, right? Think about that. In this ratio about performance, we have the design of an evaporator versus all the heat gain that must be, the heat that must be taken out from the system, okay? Heat gain is formed or composed by a lot of insulation walls, the presence on what we call vacuum insulated panels, all the footprint or the size of the product, you know. This is is affecting the heat gain. And the energy is pretty much how we orchestrate the system in order to remove that heat, okay? And deliver food freshness with the right temperatures, and so on and so forth to the system, you know. So it's an intertwined, I would say, connection between heat gain and energy, because heat gain makes a cut to be part of the energy equation here. And this point is very important. Heat gain quantifies how much heat enters into the system. Energy quantifies how much work the system performs to remove it. All right? It's a balance here. And moving forward here, now a little bit deeper into the heat gain. It's not only about the construction of the product itself in terms of wall thicknesses, because we have some insulation layer inside those A, B, and C, and D walls, you know, that's a polyurethane foaming. That's what we got in terms of insulation in the product. So the product dimensions matter, but on top of that, we also have the type of blowing agents, the formulation of this foam that goes inside this enclosed volume, you know. And we can either use cyclopentane or HFO. What's the difference? One is more efficient than the other. HFO is more efficient, 30%-ish than cyclopentane, but it costs more. It's all about the entrapment of those gases into this kind of cellular structure from the foaming, that makes the HFO to have such a lower thermal conductivity and therefore better insulation performance. And also the way that we pack the foaming, right? The underlying process, right? We can have single port, that's a single port in terms of injecting the foaming from the bottom of the product, and the foam is going to grow to the top, or multi-port, several ports where we're going to inject foam in the product. And last but not least, the presence of VIPs. It's not a very important person here. He's a vacuum insulated panel, right? So we use that to boost the insulation in some walls where we need very thin walls, so that you can increase capacity, but you can guess what? It comes with a cost, okay? And VIPs are likely to be 10 times more efficient in terms of insulation than the regular foaming, right? You can see the benefit of that, but it costs. They are expensive. Now going into more details about energy itself. From a system level perspective, talking about heat gain, and by the way, there's a physical test that you use to validate the heat gain model. It's called reverse heat leak. That's the way you collect physical test data to validate the simulation model through this reverse heat leak test, But heat gain now is one of the input variables for the energy, right? It turns out to be an input variable to energy, right? But on top of that, the second part on the COP ratio from a refrigeration standpoint, right? We have the control boards in the software, the control logic. We can have multiple types of compressors, right? The heart of the system here. We can have multiple fan motors to deliver temperature distribution so that we can really deliver food freshness in a very stratified way to both compartments. And last but not least, heat exchangers, in this case condenser. Think about all these different types of components, all the different parameters that you can take into account from a control logic perspective, all of those things together to deliver the system level performance here. And then one very important requirement, we can deliver capacity at the right energy consumption, that can be Energy Star, but we cannot penalize what we call robustness. I don't want external sweating on the walls, I always want to have a positive delta between the surface temperature and the dew point. Otherwise, there will be some external sweating. As you can see in that picture from a water dispensing portion, imagine in your house is happening that. You don't want that. Very important. There's a robustness. There are some other robustness requirements from a refrigeration standpoint, like frost formation or internal condensation. This is one of the biggest for us, external condensation. And of course, this cannot be taken out, right? We always want to minimize this, right? You can have a lot of VIPs everywhere, but can we pay for that? Can we make this product competitive? That's always a challenge in place here. So we have the cost of insulation and the cost of cooling components, right? We call this compounding cost, that's summing up both of them as the architecture cost, okay? So the architecture cost must be minimized with a given weight in terms of penalizing the objective function so that you can optimize the whole system, okay? So moving forward, these are other things that we are working on that can be also taken into account for the model, okay? We want internal distribution for the airflow, right? Air delivery to the product or airflow management. Structural stiffness. Imagine your product's fully loaded with a lot of food storage on the door beams, and the cabinet should be withstanding all that load without any distortion, so that you can, if that happens, you can lose insulation, and the gaskets are not going to compensate, and there will be some trade-off in the heat gain. That's going to affect energy. Everything is connected here. In packaging, we don't want to deliver, the NVH, noise vibration harshness, the airborne and structural borne noises. Foaming simulation, as you can see there. This is a single port foaming injection through the bottom deck of the product, as an example for that picture. That's a simulation model. And we want to pack the whole foaming. And you can guess what? If you have very thin walls, the foam is going to be very obstructed to go smoothly. And therefore, there's going to be a trade in terms of feeling. And therefore, it's going to create some kind of internal voids, and therefore, there's going to be likely to have external condensation. Okay, everything's traded here, is intertwined. In packaging, we want to deliver products to the customers without damages from transportation or handling. Okay? A lot of VOEs, voice of engineering or system level requirements that must be harmonized, and they are highly dependent on several input variables. Okay? talk about the trade space, input variables. This is real, okay? This is exactly what we've done more recently. There is one product that we use this type of approach more recently. 34 factors with 2 levels. What is that? I can have thickness with thickness A and thickness B, 2 levels, that factor. Or the presence of a vacuum insulated panel, foaming or VIPs, okay? That's is like a 2-level settings for factors. But I don't have only 1 or 2 that makes 4 runs, overall. I have 34, okay? There are 3 factors with 4 levels, okay? Control boards or condensing systems, or type of foaming properties. And 1 factor with 5 levels. If we try to account for all the possible combinations, we are talking about 55 times more than all the stars in the galaxy. 5.5 trillion of combinations, okay? It's a lot. Can we handle this even with HPCs or high performance computing? It's not something we can handle, right? That's why we come up with this kind of approach, which is called Whirlpool Tester Recommender, okay? Founded by or grounded in Six Sigma, okay? Where we use design of experiments approach or orthogonal arrays, okay? It's an application that is spinning in AWS using Elastic Beanstalk, where we have R and Python at the back end, right? And we have this type of tester recommender so that there are 2 questions that we need to answer, and it is going to come up with the right recipe that we have to start with, okay, in terms of priority. Why is that important, orthogonal arrays? Because this is the most efficient way of collecting the data in a pairwise, balanced, and independent way in the trade space. Undoubtedly, that's the best way to collect the data. You can do space filling design, random sampling, whatever, but this is still the best way because it's fully balanced, is orthogonal. That means that there are no such correlations across the input variables, right? Collinearity issues. And this is, you have a pairwise. What's a pairwise here? 1 level setting for any given factor will at least be crossed with all the level settings for all the other factors, pairwise combinations. It's going to cover the whole trade space, okay? There are some techniques that we use here in order to have the initial coded design that we call. We do some wrangling on that, okay? Some automatic techniques that we have embedded to this approach here. And we come up on what we call initial uncoded array. And we use that to fit the model, the machine learning model, okay? And as a machine learning, what we normally do, we use a lot of regression models. We start with the most simple model because this is an orthogonal array. I can use linear regression because multicollinearity is not affecting us a lot, right? Even though I have this holdout sample from the test set, I can still start with linear regression in this case here, right? If the model is not good enough in terms of accuracy, okay, for the cross-validation or the training set, we do what we call augmentation. But on the way that I run more, we normally proliferate more runs that are easier to run. Energy runs, they take seconds to run, or 1 minute to run an energy run. I can produce thousands of runs in few hours, okay, for energy. Heat gain models, they take hours to run, okay? So I can do augmentation on the energy side and rely on the groundwork given the orthogonal arrays for the heat gain runs, that's the data augmentation, if needed. I can tell you that I still didn't see a sampling plan using this technique that was surpassing 1,000 runs, okay? Compare 1,000 versus 5.5 trillion, okay? And it's covering the inference space, is allowing us to do the CI/CD for kind of model, checking the accuracy of the model, with accuracies above 95% for all those response variables here. All right, efficient DOE sampling reduces the unmanageable design space into a tractable and effective data set used to train machine learning models. We make this tractable to run. All right, so once we have all those models in place, right, we can do inferencing, we can do predictions using those machine learning models because they passed all those safeguards in terms of accuracy for the held out set, which is the test set, but also they were optimized for the cross-validated training set, and now they are available to run what we call optimization. Optimization, very, very effective and efficient type of approach here that's based on multi-objective genetic algorithms, okay? you can see the MOGA thing here, multi-objective, is because we have energy, cost, capacity, cooling, robustness. There are multiple response variables to be tackled here, right? And those are the key steps we have in place. Constrained population generation, that's the first step. What is that? Not all the runs are feasible, okay? Some runs, inherently, they are not going to survive. From just at the beginning, to collect the data, sometimes I cannot even calculate the energy because I'm not kind of delivering the minimum temperature that must be delivered to the product. So those runs are eliminated, okay? Those are voids that we have in the data set itself. There are some other linear constraints we have in this data set, like if there's a marketing requirement, the wall thicknesses from both sides must be the same, or doors flushness, right? I can have a door depth from the freezer as a parameter, which is different from the door depth from the refrigerator. If you look at the product, you can see a lack of flushness, right? Is this something desirable from a market standpoint? No. So we add a lot of linear constraints or variable linkages here. That's what makes the constrained population generation. So we only generate the population for whatever is feasible, okay? Step number one. Step number two is performance prediction here. So remember, before we had all those machine learning models that were working well with a good degree of accuracy, and now they can be used to pick out that initial sampling and do inferencing, right? Calculate the predicted results. Step number three here, evolutionary selection. Think about the way it works in genetics, right? If we have a gradient descent, it's gonna very likely give you a local optima. Why? Because it's all about the way you start collecting the data. Okay, it's gonna converge to a local optimal. But you don't know whether or not there are some other optimums in your inference space that could be further explored. This is addressed with this approach here, because genetic algorithms, they are going to exploit locally, and they're going to explore away from the inference space on other portions of the inference space. So exploiting is an analogy for crossover. Exploring is an analogy for mutations. That's why they are called genetic algorithms, because of this inherent nature to exploit and explore, right? And do this several times until you find something that's really delivering what it takes to converge from a Pareto front perspective, with the best balance across all those desired outputs with a given set of weights or importance. That's a way to penalize the objective function, right? By setting up some weights. Because cost can be more important than capacity depending on the needs, marketing needs. You can always balance that with a given set of weights. And when you get that, you have the final weighted composite score that we use to define the best solutions, okay? So again, feasible runs, do the inferencing for that initial population, do crossover and mutations, find the optimum from a well-balanced perspective here. And now I'm gonna go in details about the diagrams here, right? Very important thing to talk here, right? How we do that in AWS. I'm gonna spend a few more minutes here on this one to go to exactly the details about this structure here. So think about that. The first element you see right there is an API gateway, very modular. There's an API call that can be used in any applications we have in production, Using Elastic Beanstalk, you can consume this diagram in terms of an API call, so that we can use this to do optimizations or model fitting or tuning here. So this is fully orchestrated by API gateways and a Lambda. That means it's a serverless approach, right? You can use as needed, okay, with zero overhead, all right? Very modular. One core element, as you can see, is the piece that's called ECR there. Look at that. Is all the way to the right-hand side. It's an elastic container registry with an image, a container image, that's taking into account an entry point from the container. Of course, within the ECR, there's a Docker file, a requirements.txt, and a dynamic loader. Why I'm not using here a pre-packed kind of training job from SageMaker container? Because they are limited to either scikit-learn or deep learning. I want all of them plus optimization, okay? So that's what it takes to build a customized container for this approach, because it's gonna fulfill all the needs for this workflow here, right? And you can see that's an S3 bucket pointing to the ECR image there. It's a dynamic loader. Those are, that S3 bucket contains a file that's called training main that's going to route that file with all the instantiations for the SageMaker training jobs within the entry point that belongs to this ECR, right? And therefore it's going to subsidiate the Lambda to trigger the SageMaker training here as needed, all right? So after the Lambda is triggered, there's a key indicator that you can see yellow color there, operation type. This guy here, okay? This is an environment variable within the Lambda function here that orchestrates the whole thing that can distinguish either it's gonna do the model training or fitting or the model tuning. As you can see on the top, it flows to the model training, and at the bottom, it flows to the model tuning here, right? If the user at the front end is gonna click on the model training, what's gonna create for us? It's gonna orchestrate the Lambda by parsing all those parameters, you know, and the ECR with the container image to trigger the SageMaker job so that we are gonna fit the models and we are gonna create pickled files for the model fitting itself, because we don't want this, we want to front load the model fit. I don't want on the user side, whenever you open the application, the application is gonna fit the model for you, it's gonna take all the time to fit the model. I want this to be packed, to be front loaded. And very important, there's another file here within this model train that's called Shapley or model explainability, okay? Because it's part of the application to have explainable AI. One time, maybe some years ago, we used to say that neural networks are kind of black boxes or models are black boxes, but Shapley values came to rescue us in terms of AI explainability. This is also front-loaded for the model training here. When I say Shapley values, I'm talking about Pareto of importance, right? And partial dependence plots that shows the direction of change. If you change from thickness A to B, what's going to be the hit gain kind of impact, you know? You can see all those explainable AI graphs into these two files that you can see on the top right corner in terms of that output S3 bucket for training. Now talking a little bit about the model tuning, right? We can trigger the Optuna, is the library that I use to train all those models, right? To do genetic algorithms, to the same algorithms that we use to train to create the optimal architecture we use to hyperparameters tuning as well. Same thing, same thing. It's just a way to instantiate this differently, design factors and hyperparameters for a given model, you know. There's a bucket that points to the tuning process here that contains all the tuning configurations, a JSON file that takes into account all the, if it's a deep learning, you name it, you know, number of neurons from the first layer, number of neurons from the second layer, is there a dropout, do we have batch normalization and many others, okay, or the learning rate, you name it, right? All those things are going to be taken to this modern tuning standpoint, you know. And the tuning itself is going to create kind of the best balance in terms of tuning results. It's a pickle file at the bottom, S3 bucket. And once the tuning is processed, done, the user can see on the application exactly the test set accuracy, you know. If the user is satisfied with that, you go there and click the button to train the model, okay? And then we are going to front load the model training file plus the explainable AI file that we call Shapley creation, pickle file, okay? This is pretty much the architecture for this backend for doing all this orchestration. I know that's quite complex, but this is so useful, very flexible. API, you call it, consume it, it does a job on demand. It's gonna call SageMaker to do the job. You can pick whatever instance within SageMaker as you want, okay? If it's deep learning, you guess what? You're gonna require such a more powerful computing instance, right? And many other things, you know. There are 11 type of, or 12 different regressors in this approach here. Okay, I have CatBoost, I have deep learning, I have XGBoost, Kriging or Gaussian process regression is there as well. Support vector machine, everything is there. Okay, pre-packed there. And you can add more by simply changing the S3 bucket for the training code. Okay, it's just the sake of adding more. And whenever you add more, because it's an S3 bucket with versioning, you're gonna see that this API is gonna reflect that accordingly. Okay, that's the beauty of this flexibility here. Okay, before I show the video here, I want to explain a little bit. Okay, now we showed the whole diagram for the training and tuning process, you know, in a modular way, with this dynamic loader for the container itself. But how about the front-end application, which is a serverless, which is Elastic Beanstalk, you know? It's a Beanstalk app which runs within a VPC, okay, virtual private cloud here, which can be only accessed through a VPN if you're using kind of remotely, right? Which takes into account what we call auto-scaling and load balancer, which is deploying using a Docker container, okay? So if you remember on the previous slide, there is the output from the model training, it turns to be the input for this diagram here. As you can see in the bucket at the bottom, inputs, the train models pickle and the Shapley creation pickle, they, from output at the previous slide, they turn to be inputs for this Beanstalk application because they are going to be consumed into the Beanstalk application front end here. And also because there's a lot of explainable AI, EDA, exploratory data analysis and so on in terms of into the front-end application, we have the data and app resources. App resources is very interesting here because I'm not, whenever you do a Elastic Beanstalk using a container, you can, as simple as having 3 files. Application file, the Docker file, and the requirements.txt, you know, those are the needed files to really deploy an application, a Beanstalk application very easily. But that app.py file that makes the cut for one of those 3 files that are zipped and used to deploy a Beanstalk application orchestrates all the calls for these data and app resources. It's like a microservice type of architecture that we have in S3 bucket with all those packages, right? So they are dynamically called from this app.py file that resides within the Beanstalk and orchestrate this whole front end here, okay? Meaning that if we change any files within the S3 bucket, that means that your Beanstalk application, the front end is gonna see that if you restart the Beanstalk. As simple as like that. You don't need to redeploy, it's just restart the server, that's it. Because whenever you restart, it's gonna retrieve whatever is new at S3, that's it, okay? So a private VPC hosted application, internal load balancer, auto-scaling EC2 instance, application code, data, and train model artifacts are stored in S3, as you can see here in this top S3 bucket. Is a Docker-based because we want this to be prevalent and really reflect, be always containerized for the sake of functionality in a robust way. And that's it. That's the front end from this Elastic Beanstalk application. Now I'm going to showcase a video, okay, that's going to give you some more practical insights on the way that everything that we talked here was wrapped up and put together to deliver an optimal architecture here.
Our strategy is to continually improve our products. We are now showcasing our innovative in-house multi-physics optimization workflow, which seamlessly integrates VPD and artificial intelligence. Our advanced model incorporates more than 50 design factors to identify optimal combinations across multiple key performance metrics, including energy, capacity, robustness, and cost. It enables smart trade-off decisions among these often competing factors, ensuring balanced and optimal solutions. This powerful yet user-friendly engineering tool allows for real-time adjustments to various parameters, such as product dimensions, height, depth, and width, insulation wall thicknesses, vacuum-insulated panels, mullion position, compressor type, and many more, with real-time predictions. We can also run optimizations by setting appropriate targets and weights for all requirements and establishing constraints on the input variables. For instance, 10,000 product iterations within the design optimization loop can be completed in approximately 5 minutes. With this cutting-edge technology, we can significantly accelerate our decision-making process in the early stages of product development. Innovation always in constant pursuit of improving life at home.
All right, I hope it was useful to see exactly the way that we encompass all those things, all those different ways that we can visualize the data from an exploratory data analysis standpoint, you know, because Another way to check how machine learning models, they do make sense is not only about looking at the accuracy from a cross-validated training set, but also at the accuracy of the test set itself, but also if the models are delivering what they must be delivering to you, okay? And how do we do that? If we look at the correlogram, at the EDA, if there's a correlation between one response variable and one X, and you see that's a more pronounced effect in the explainable AI partial dependence plot, that means that this is making sense. The model is giving you the partial dependency plots given the Shapley file that was created at the front-loaded from that architectural diagram, but the raw data is also giving the same signal to you, okay? So we normally look at that, okay, correlations across the axis that are not a big deal for deep learning, but they may turn into a big deal for linear regression, but we always look at the EDA part with correlograms, with parallel coordinate plots, histograms with the actual model results, 2 layers, EDA plus a explainable AI, and also some other layers for prediction to do inferencing, from a prediction standpoint. And the last but not least is design optimization. Design optimization here takes into account what? The genetic algorithm, and you're going to set up a lot of different weights across all the response variables. You can select if you don't want, I don't want to optimize heat gain, I want to optimize energy, right? Because heat gain is an input for energy, right? We can have this selection about not caring about heat gain, do not optimize, but caring a lot about energy, and we can either optimize to minimize or maximize, or to reach a given target. For internal capacity, we want to be very straight to the target, okay? I want that given capacity with such a very high weight, okay? So we are going to force the genetic algorithm to really explore, because it takes more emphasis into account, more weight, right, into account. And then we can also, for robustness, for external condensation, I don't want to have external condensation, right, but I want to have at least a delta from the surface temperature to the dew point that's 1 degree, okay, that's it, okay? So at least 1 degree, greater than 1 degree. So it can be greater than, can be straight to the target, can be do not optimize, can be maximize or minimize, okay? And you can select exactly which factors at their respective levels that you want to optimize. There was a study that was done that we didn't want to optimize the product with vacuum insulated panels. We just unflagged them, okay? Because they are categorical variables with discrete level settings, right? Just unflag them and force the exploration space to only to look on what you want, okay? This is fully democratized and deploying Beanstalk and available to use to the enterprise here. And the last here is one last slide. What's in there for Whirlpool, is AWS SageMaker. We estimated up to 70% in terms of efficiency here, with much better effectiveness here in terms of model training and tuning. Such a modular architecture that can be consumed in any applications, right? And therefore, because you can pick whatever instance EC2 makes sense to you, you can expedite a lot, even very complex machine learning models like deep learning ones, okay? So up to 70% benefit for model training and tuning time, and up to 95% at least for architecture definition. Imagine doing all this massive work manually, okay? Try to come up with a sequential approach to multiple design of experiments with only few level settings to try to incrementally do all this exploration and try to come up with an optimal. If you don't do the right algorithm, you're going to converge to a local optimum that's going to be suboptimal, With this approach, you can explore and exploit and converge, okay, with the right emphasis or weight for whatever makes sense in terms of desirability for your design, okay? And this is giving us a lot of leverage in terms of effectiveness and efficiency for product development. That's what it takes to really define a winning architecture, because from a systems level perspective, architecture drives behavior, okay? If you have the right architecture, everything is going to flow naturally, it's going to be more resilient, your life cycle or digital thread is going to be more sustainable upfront. All right, with that being said, that ends the presentation here. I thank you so much for being here to listen to us here today, and I appreciate we can have some offline conversations here, and Saurabh and I will be more than glad to really answer any questions that you may happen to have. All right?